In 1875, a French politician gazed at a broken copper sheet and saw the impossible: a 151-foot colossus would rise on Bedloe's Island, a gift from France to America, assembled piece by piece without a single power crane or modern tool. No pneumatic drills, no hydraulic lifts, just hand-forged rivets, wooden scaffolding, and men who trusted their lives to rope and iron. The Statue of Liberty was not supposed to be possible, yet crews fought wind, weather, and the relentless Atlantic to bolt together a monument that would stand for centuries. How did they conquer an engineering challenge that had never been attempted before without the machines we take for granted today? The answer begins with a vision so audacious that most engineers called it mad, and a sculptor willing to stake his reputation on a dream that seemed to defy every limit of 1880s construction. Gustave Eiffel, already famous for his revolutionary iron towers, faced a problem no builder had solved before. A copper statue standing as tall as a 15-story building had to be strong enough to withstand Atlantic gales that could exceed 60 miles per hour. The winds alone would twist and tear any structure not anchored in absolute iron discipline. The torch arm would sway in the wind, threatening to snap at its base. The crown would rock side to side, testing every rivet that held the copper skin to the interior framework. Worst of all, the entire weight of the monument, over 450,000 pounds of copper and iron, had to be supported by a pedestal, an internal skeleton that could flex with the wind rather than fight it. Eiffel's solution was a network of iron bars crisscrossing the interior, a framework that allowed the statue to move in the wind without cracking. The design demanded precision at every joint, every connection engineered to absorb movement while resisting the constant assault of the elements. In the workshops of Paris, teams began the painstaking process of hammering copper sheets by hand. Each sheet was shaped over wooden forms coaxed into curves that would eventually form the statue's robe, face, and hands. No hydraulic presses shaped this copper. Instead, workers wielded hammers for hours, striking the same spot thousands of times, watching the metal slowly yield to the rhythm of their labor. The sheets were thin, less than 1/10 of an inch thick, making the copper flexible enough to bend around the interior frame while strong enough to resist the elements. Artisans worked from plaster models created by the sculptor Frederick August Bartholdi, translating his artistic vision into copper with nothing but traditional metalworking techniques that had changed little since medieval times. The interior iron framework grew in Paris under Eiffel's direct supervision. Massive iron bars, some as thick as a man's leg, were cut, heated, and forged into position. Every connection was riveted by hand, the same technique used for bridges and ironclad ships. Heaters crouched beside coal forges, pulling rivets heated to cherry red, tossing them through the air to catchers perched on scaffolding. The gunmen followed with pneumatic hammers, driving each rivet home in seconds before it could cool. This process repeated thousands of times, each rivet locked in by the strength of a man's ability to control a mechanical hammer. The interior skeleton that would hold the statue together for eternity was assembled in Paris. Tested, disassembled into 214 separate pieces, and carefully crated for the journey across the Atlantic. The voyage itself was an odyssey. French ships carried the disassembled statue through rough Atlantic waters, each crate lashed down and prayed over as waves crashed against the hull. Crews on the deck secured loose cargo, watching for the shifting motion that could crack the delicate copper skin packed inside. For weeks, the statue's pieces were nothing but heavy freight, valuable only for the dream they represented. When the crates finally arrived in New York Harbor in June 1885, the real challenge began. There was no place on Bedloe's Island to assemble the statue in one piece. The pedestal was still under construction, a massive granite and concrete base that took longer to build than many expected. So the copper skin, the iron framework, and the internal structure all sat in crates for months, waiting. Workers began the assembly in the spring of 1886, starting from the feet and working upward. The iron framework was bolted together first, joint by joint, creating a skeletal giant that looked like nothing so much as an industrial nightmare. Crews working on temporary wooden scaffolding bolted the iron bars in sequence, checking alignment with plumb bobs and chalk lines, the same methods used on every skyscraper and bridge of the era. Once the framework stood, the copper skin began its ascent. Sheets were hoisted by derricks and small steam-powered cranes. Pieces of the robe, the arms, the torso, all fitted to the iron skeleton beneath. Every sheet had to align perfectly with its neighbors. Gaps or misalignments would let wind in and weaken the structure. The riveting process on the statue was more delicate than on bridges or buildings. The copper skin was thin, easy to damage. Heaters positioned themselves inside the framework, heating rivets in portable forges, while catchers and gunmen worked in cramped spaces barely wider than a man's shoulders. The work was hot, suffocating, and demanded absolute precision. A rivet driven at the wrong angle could pierce the copper skin or crack the sheet. Workers inside the statue often labored in total darkness, guided only by the glow of red-hot rivets and the shouts of foremen relaying instructions from the outside. The space inside grew increasingly cramped as the statue took shape. By the time crews reached the crown, workers were contorted into impossible positions, driving rivets in spaces so tight that only the thinnest men could squeeze through. One of the most dangerous phases came when the torch arm had to be attached and aligned. The arm weighed several tons, and it had to be positioned at exactly the right angle, both for structural integrity and for the aesthetic vision Bartholdi had created. Crews hoisted the arms section by section, bolting and riveting it to the shoulders as wind threatened to catch the copper and tear the whole thing off. Men balanced on narrow iron bars hundreds of feet above the water, holding taglines and guiding the massive pieces into position. A slip, a sudden gust, or a failed rivet could send the arm swinging like a pendulum, throwing men from their perches or snapping the connections beneath. The face was assembled last, the individual sheets of copper, representing the statue's features shaped and fitted together like a three-dimensional puzzle. Workers inside the head, a space so confined that movement was nearly impossible, hammered rivets connecting sheets that formed the nose, cheeks, and jaw. The eyes, windows of sorts designed to let visitors look out onto the harbor, had to be positioned precisely. Getting the proportions right demanded artistic judgment and mechanical precision, working in perfect harmony. Master craftsmen trained in the traditions of European metalworking directed the work, ensuring that the statue's features matched Bartholdet's vision, even as it was being assembled in pieces. The wind was a constant adversary throughout construction. The open framework of the statue, before the copper skin was fully attached, acted like a sail, catching gusts and threatening to topple the entire structure. Crews had to stop work whenever winds exceeded 40 miles per hour, which meant frequent shutdowns, especially as autumn approached. The Atlantic hurricane season added another layer of urgency to the work. Any major storm could damage what had been built, forcing crews to start over. Workers lashed everything down with rope and cable, creating a web of temporary bracing that looked chaotic but was precisely calculated to resist the forces of wind and weather. The internal bracing system Eiffel designed proved crucial. Horizontal iron bands circled the statue at regular intervals, connecting the vertical framework and distributing the stress of wind forces across the entire structure. The framework was designed to flex, to sway slightly in the wind rather than stand rigidly. Modern engineers have confirmed that this design was years ahead of its time, anticipating by decades the principles of flexible structures that would later revolutionize skyscraper design. Workers didn't fully understand why the design worked the way it did, but they trusted Eiffel's calculations and followed his blueprints with religious devotion. As October 1886 approached, the final pieces fell into place. The copper skin was complete, the torch was in place, and the internal framework was locked solid by thousands of rivets, driven by men who had poured months of labor into the work. The last rivet was driven with ceremony, photographers capturing the moment that the statue became whole. Within days, President Grover Cleveland was on a boat heading to Bedloe's Island, ready to officially dedicate the monument to the American people. The Statue of Liberty, assembled from pieces without modern tools, without power equipment beyond a few small derricks and steam engines, stood complete and ready for its role as the greeting that would welcome immigrants to America for generations to come. But the real test came in the years after dedication. The statue had to survive not just the initial construction, but decades of exposure to the Atlantic's salt air. The freeze-thaw cycles of winter and the relentless humidity that corroded iron and turned copper green with patina, the riveted joints, sealed only with red lead primer, and the overlapping of copper sheets, had to remain watertight. Maintenance crews discovered that the work had been done so well, with such care and precision, that the structure required far less repair than anyone had expected. The rivets held, the joints remained sound, and the internal framework resisted the elements year after year. Nearly 140 years after its dedication, the Statue of Liberty still stands, a monument not just to American ideals, but to the skill and dedication of craftsmen who built it without modern power tools. Visitors walk through the interior, climbing narrow stairs and squeezing through tight passages, never fully understanding the effort it took to assemble this monument. They see the torch raised against the sky and imagine the moment it was first lit. But few realize that the torch arm was hoisted and riveted in place by men on narrow iron platforms hundreds of feet above water, with nothing but ropes and skill to keep them from falling. The Statue of Liberty remains a testament to what human ingenuity can accomplish. When vision and craftsmanship align, engineers today study the structure, analyzing how Eiffel solved problems that wouldn't be formally addressed in engineering textbooks for decades. The flexible framework, the careful distribution of weight, the understanding of wind forces and material properties, all of it was worked out in the 1870s and 1880s. Without computers, without stress analysis software, without the mathematical tools modern engineers take for granted. Today, nearly 4 million people visit the Statue of Liberty each year, climbing to the crown, looking through the torch windows, standing in the presence of a monument that represents freedom and hope. Few of them realize that what they're experiencing is a building assembled by hand, riveted together one at a time, hoisted into place by men who had no safety nets and no second chances. The monument stands as proof that human determination, combined with skill and vision, can create structures that transcend their era, outlasting the tools and methods that built them. As we face our own architectural challenges in an age of automation and machine precision, the Statue of Liberty reminds us that progress built on human skill and sacrifice often proves stronger and more enduring than anything created purely by machines.